That's it, yeah. Okay, well, let's go ahead and get started. Just as a reminder, yeah, this coming Thursday will be early, probably about 11:30. I've got a surgery Thursday afternoon, so we'll cut class out early, and then we'll pick class back up the regular place, regular time next week at 8:30. So we'll be good to go. The 29th. Yeah. That's,
and when does the actual pipeline start?
I'm sorry?
The paramedic pipeline, the actual...
Oh, the pipeline will start with ECG interpretation. That'll be the next class after this.
Wait, what date is it?
Check the syllabus. Yeah.
It's the 10th.
Whenever.
That's what I couldn't...
Yeah. Whenever this class ends, that one begins. The beginning of September. The first, second week of September. You just check the...
I think it shows the 5th we end this one, and the 10th we start.
Yeah, that'd probably be about right. Yeah. And that's when everybody, the whole course will be, right? All 13 people or so. So that's when we will have to talk about the well, I've talked about the portfolio already, but that's when you guys will actually get training on Platinum Planner and actually start engaging with the clinical portfolio that we'll actually all have to document. Okay. So with that in mind, let's go ahead and get started. So how are you guys doing on fluid electrolyte balance? Hopefully you had the weekend, took some time to study, go through it. Do you have any questions over any of the concepts that we went over last week? I did get the videos posted and put into Canvas for you. Good thing about those, you can listen to them as well, so you can just do YouTube as audio. You don't have to sit there. I mean, you sit there and actually watch, and you just do the audio if that works for you. I believe Anna's working on getting everything up in podcast form as well. It's just a matter of getting college to pay for it, because we need a host. We need a site that'll host it, and then we can put them up through the regular podcasting venues. The one that we looked at would only let us do one free podcast a week, and clearly that's not enough to cover the content that we've done so far. So she's still looking into that, but in the meantime, I'll continue recording these and putting them up, because they are putting up the more complex ones. Acid base and fluid electrolyte tends to be pretty complex. Okay, so before we move on to acid-base balance, I want to do a little exercise with you all to just show you how powerful the quantitative basis is that we've developed thus far. And so what I want to do is I want to pass these around.
Sounds good.
And just have enough for every person, but you guys can just kind of share and take a look at them. So what do we have here? What did I just pass around to everybody? Okay, normal saline, right? So what I want to do is I want to go through an exercise to demonstrate where all this comes from. Now, I assume, because you all are intermediates or advanced EMTs, that you do lots of IVs and you hang lots of sodium chloride, lots of normal saline, right? Here's a question: how well do you know that sodium chloride that you supposedly hang and use all day long? Probably not very well, I would surmise, right? So let's dive into this a little bit and now use the foundation of fluids and electrolytes that we've developed to understand IV solutions in a little more detail. So I'm going to use sodium chloride, or 0.9% sodium chloride, as an example of that. But we could do that with any other common solution that we carry. This one just happens to be fairly easy to do. All right, so let's take a look at this. So if you guys take a look at the bag, I want to know how. So first of all, you remember what a milli equivalent is, right? What is a milli equivalent? What is a milli equivalent? An MEQ.
Set. Mol.
No, milliequivalent's not moles times charge over liter. Not a milliequivalent. No, you're in the right direction, but that's not. No. Good. A milli equivalent is 1/1000th of an equivalent. Right? Of an equivalent. An equivalent is 1 mole times 1 charge plus 1 or minus 1 charge divided or in a liter of water, right? That's equivalent. So we say that there is one equivalent of a substance dissolved in water. That would be 1 mole of a substance that has a plus or minus 1 charge dissolved in a liter. That makes sense? And we typically don't deal with concentrations of electrolytes this concentrated in biochemistry and biology, human physiology. So we take a thousandth of this. That's a milli equivalent, right? So 1 equivalent would equal 1,000 milli equivalents. Does that make sense? Okay. So the question I want to pose is, let's look at that normal saline that I passed around, and I want to know how many milliequivalents of sodium and how many milliequivalents of chloride we have in that IV bag. It actually says on there.
8,
Huh?
8 and 8, or it says.
Just look at the IV bag. Don't guess. Just look at it. It tells you.
It says, I think I misread
It tells you right on the back how many milliequivalents of sodium and how many milliequivalents of chloride do we have in that bag.
50.
4.5 to 7 milliequivalent of sodium.
Say again?
4.5 to 7.
It's pH, I think.
Yeah, it's.
So I think it's.
How many milliequivalents per liter of sodium is there, and how many milliequivalents per liter of chloride is there in that bag? That's.
Oh, 154.
Oh, there you go.
154 liters.
Yeah, you don't have to guess. It's right there on the bag, right? So you guys see that? Right there?
I don't
Okay.
even see that either.
Go ahead and show these two up front on that bag there.
It's about 1, 2, 3, 4 lines down. Where it starts with 250 mils, where yours says 15.
Yeah, we have 50 mil bags.
But it's probably about 4 minute lines.
Yeah, go ahead and take a look at the bag there. So, in
That's
that-
what I think that's the number I was referring to with that one. Cause it said
Okay.
8 and 8 or something, right? This says 154,
okay, good.
sodium 154, that one says sodium 8, right?
All right, so I got sodium,
So,
I have 154 milliequivalents per liter, right? And chloride, I have 154 milliequivalents per liter. Right? That's what I have dissolved in that. And remember, the sodium chloride starts out as a sodium chloride molecule, right? Ionically bound. But what happens is when I put the sodium chloride into water, remember the water molecule is very polar, and the oxygen part of the water molecule is more negative than the hydrogen part, right? And so when that sodium chloride goes in the water, what happens is that because the sodium tends to give up electrons, the chloride tends to take electrons, the chloride becomes attracted to the hydrogen part of the water, right? Does that make sense? And then the sodium becomes attracted to the oxygen part of the water molecule. Does that make sense? And that molecule of sodium chloride breaks apart. It's known as dissociation. It dissociates in water. And when something dissociates, in water it dissolves, right? I.e. it gets dissolved. All right, so when we put 154 milliequivalents of sodium chloride, right, into a water, the sodium chloride will then dissociate into 154 milliequivalents of sodium and 154 milliequivalents of chloride. And does that make sense? Why? Because the water is polar. Okay, good deal. Okay, so let's start there. So now what I want you guys to do is I want you to pull up your periodic table of elements. We keep referencing that, but and I'll pull up the periodic table of elements that I gave you in pharmacology, because that has the atomic weights, because we're going to get molar and deal with Avogadro's number here a little bit. Cool. All right, so let's start with sodium first. So what is the atomic mass of sodium?
2.99,
Do you guys see that there? 22.9?
95.
95. Yeah, how about we just do, 22.99, right? Just round it up. All right. So the atomic mass of sodium is 22.99, we'll say. And what that means is 1 mole of sodium would give you 22.99 grams, right? So 1 mole of sodium, or 1 Avogadro's number, which is 6.02 times 10 to the 23 individual ions. So 1 mole equals 22.99 grams. You guys okay with that? Okay, so let's move over to chlorine now. What is the atomic mass or atomic weight on chlorine?
35.45.
So 35.5. You guys okay with that? If we just kind of round a little bit. So the atomic mass for chlorine is 35, right? 35.5 gram, or 35.5, right? And so if I have 1 mole, or 1 Avogadro's number of chloride, I'd have approximately 35.5 grams. You guys okay there? Okay, cool. So let's just continue with these calculations here. So what I want to do is I want to know how many grams of sodium do I have in that liter of sodium chloride, that liter of normal saline. Is there a way of calculating that? Is there a way of figuring that out from this?
Dividing by 1,000?
Or multiply by 1,000 and then kind of reverse engineer that.
Okay. Couldn't I just do a dimensional analysis here? Remember in pharmacology, we talked about the dimensional analysis and a dosage calculation? Isn't this a similar question? So, what do we know for a fact? Let's start there. What do I know for a fact?
154 MEQs per liter.
Okay. Well, I know yeah. But I want to know how many grams that is, right? So that's part of what I want to know. But what I know for a fact is 1 mole of sodium, 1 mole of sodium equals 22.99 grams. Would you guys agree that we know that, right? We looked at the periodic table. Okay. And what do I want to know? Well, I want to know how many grams I have with 154 milliequivalents. You guys okay with that? 154 milliequivalents. Now, what do I have to do with that 154 to make it work with this formula? And I think you mentioned it earlier. Huh?
Multiply by 1,000.
Not multiply by 1,000, but divide it, right? So 154 milliequivalents is how many equivalents? Well, yeah, 0.154. You guys okay with that? So if 1 mole equals 22.9, 0.154 equals X. You guys okay with that? Does that make sense? How I put? So now all we gotta do is just cross multiply and solve for x. So 1 times x is just x, right? All right, so x falls out equals, and what's 22.9 multiplied by 0.154?
3.5.
3.5, you guys okay with that? So x equals 3.5 grams. So if I have 154 milliequivalents of sodium, that gives me 3.5 grams of sodium. You guys okay with that? Now that's not going to be the same for say calcium or potassium, right? Because they have different atomic masses, and an Avogadro's number or a mole of those is going to have a different weight. Does that make sense? So it's going to be different for every other element or every other ion. But 154 milliequivalents of sodium is 3.5 grams. You guys okay with that? Okay. So let's move on to chloride, and let's do the same. So I know that 1 mole of chloride is 35.5 grams. And I want to know 0.154. Again, converting milliequivalents into equivalents is x grams. And we'll do the same thing. We'll cross multiply. 1x is x equals, and if someone wants to do the math, what is 35.5 multiplied by 0.154?
5.5.
5.5, you guys okay with that? That's 5.5 grams. So if I have 154 milliequivalents of chloride ions, I have 5.5 grams. So let's just go ahead and add these together. What does that give me? What is 5.5 plus 3.5? That gives me 9 grams. So 154 milliequivalents of sodium chloride is a total of 9 grams. You okay with that? So I have 9 total grams of sodium chloride per liter of IV solution. You guys okay with that? So let's figure this out. What does this convert to in percentage? Well, what's percent in medicine? Percent always equals grams in 100 milliliters, right?
That's where you get the 9%.
0.9%.
And that's where we get 0.9. Have you guys ever wondered where we actually get that? So we just started at milliequivalents and worked our way to percent, right? So 9 grams per liter is equivalent to saying 0.9%, right? Does that make sense?
So the 3% would just be 3?
So 3% would be 3 grams per liter. Yeah, quite a bit more, huh? If you think about it, quite a bit more. Does that make sense? So let's push this just a little bit further, on the IV solution. Take a look, and I want to know what is the osmol. Well, I think it's going to be osmolarity, because osmolality is per kilogram, but because you're, huh?
308.
308. You guys see that there? So the osmolarity,
What's this?
the osmolarity of that is 308 milliosmoles per liter, right? Now, that's not, osmolarity is not what we commonly look at in humans, right? In humans, in plasma, we commonly look at osmolality, which is not milliosmoles per liter, but rather per kilogram. But in fairly dilute solutions, they're pretty similar, right? We can use them almost interchangeably. And just remind me, what is the normal osmolality of human plasma? What's considered?
275 to 295.
Yeah, 275, 295, 275 to about 300, right in there. You know, there's a little bit of wiggle room. And that's milliosmoles per kilogram, but we know that these are gonna be fairly similar, right? Osmolality and osmolarity are gonna be fairly similar in human beings. And so what do we notice? We notice that the total concentration of solute is very similar to the concentration of solute in blood plasma. It's just a tad higher, right? And this is why we say that normal saline is isotonic, right? It's not perfectly isotonic, right? But it's fairly close. Does that make sense? You see how we got that?
And then, so the half normal saline or 3%, that's hypotonic?
Yeah, half normal saline would be 0.45%, right? So it would be half as concentrated as this. And then 3% is almost, well, a little over 3 times as concentrated, right? That's hypertonic. That's why it's often referred to as hypertonic saline. And then you also have something called lactated ringers, right? Ringer's lactate, also known as Hartmann solution. Lactated ringers is a little more complicated because it has multiple things in it. It has like 130 milliequivalents of sodium per liter, 4 milliequivalents of potassium per liter, 2.7, I believe, milliequivalents of calcium, 109 milliequivalents of chloride. It has about 28 milliequivalents of lactate. So it has several things. And its osmolality is like 275, 273, 270, right in there. So it's a little on the lower end of being isotonic, and normal saline's a little high, on the higher end of isotonic. And lactated ringers kind of belongs to a class of solutions known as balanced solutions, where they have multiple components in them that kind of reflect the multiple kinds of electrolytes that you would see in blood plasma. There's also something known as plasma light, which is another solution very similar to lactated ringers, which is a balanced solution. And there is some evidence that suggests these balanced solutions may be a little better in certain patients. It's definitely not clear, but there are a lot of people that they're becoming concerned about normal saline. And normal saline has long been used as the go-to agent that we give to people, particularly if we're going to give large volumes of fluid. And we're starting to find that may be problematic. It may cause inflammation. It's actually acidotic. We'll talk a little bit about that later on as to how normal saline can be acidotic, but it can induce, it's not literally acidotic, but it can induce acidosis. It's something called hyperchloremic acidosis that can happen if you give lots of normal saline. And so there are a lot of services that are moving away from normal saline and going to more balanced, like they're using lactated ringers, plasma light, right, these balanced solutions. So that may be something you guys may run into. There are some services, that's all they carry, they just carry LR. Other than for mixing, right, if you have to mix drugs, obviously, manufacturer will recommend or will say you have to mix, like amiodarone has to be mixed in, say, D5W, right? Well, then you carry your bags for mixing, but your primary fluid that you would hang would be something like lactated ringers and plasma light. So just kind of something to think about. So does that all kind of make sense? And I know it seems somewhat academic and superfluous, and in some sense it is, but I find it very liberating that I can look at a bag of IV fluid now and go, oh, I know what all these numbers mean, right? I know where they come from. And that's just very liberating. It's very helpful to understanding, what's going on with this whole thing. Okay, so now that review's over with, I want to move into talking about acid-base balance. So we had a pretty good discussion last week about fluid and electrolyte balance. And hopefully you can see why a lot of programs actually require chemistry. Like, because these concepts that come out of chemistry are so helpful in explaining physiology and subsequently pathophysiology. But the cool thing about this class is I can kind of mix and match and integrate things, and we can kind of cover some of the most important concepts. Okay, so let me ask you a question. What's an acid? I think before we talk about acid-base balance, we better get things straight in, like, what is an acid? What is a base, right? What is an acid? Like, that's probably a good place to start. What do you think?
Something that gives off hydrogen ions in
Okay. Yeah, that's a good place to start, right? So there are actually several definitions of what an acid is and what a base is, right? So probably the first person to really develop this or come up with a way is Arrhenius, a guy by the name of Arrhenius. And this was approximately 1800, right? So we've been thinking about acids, these concepts for a couple hundred years. So, or not 1800, but about the late 1800s, rather. So about 1880, right? There we go. So about 150 years or so. So Arrhenius defined an acid as a substance that causes hydrogen ion concentration to increase when it gets dissolved in water, right? So Arrhenius said that a substance that increases hydrogen ion concentration when dissolved in water. So it doesn't make sense to call something an acid if it doesn't get dissolved in water, right? If it's not interacting with water, then the concept of an acid is not really particularly relevant. You guys okay with that? And that's a pretty good definition. And just remind me, what do I mean by a hydrogen ion? Is a hydrogen ion the same as a hydrogen atom? Is a hydrogen atom the same as a hydrogen ion? There's something different, right? What's different? Okay, what's the charge of a hydrogen ion? Positive, it's a +1. So the difference between a hydrogen atom and a hydrogen ion is the following. What is the structure of the hydrogen atom? So you've got the nucleus, right, that contains a proton. And how many protons do we have in the nucleus of a hydrogen atom? 1, right? It has an atomic number of 1, which means it's going to have how many electrons? 1 electron, right? And so in a cloud of probability around the nucleus, you have 1 electron, right? So you've got 1 proton, 1 electron. A hydrogen ion is a hydrogen atom without its electron, right? So a hydrogen ion is a proton all by itself. And in fact, hydrogen ions are often referred to as protons, right? So hydrogen ion, proton, okay, means the same thing. They're synonyms. You guys okay with that there? Okay, so that's the difference. All right, so any substance that gets dissolved in water that increases hydrogen ion concentration is what Arrhenius said was an acid. And then in the early 1900s, between about 1908 to right around 1917, okay, two scientists independently arrived at essentially the same conclusion, and these were Bronsted and Lowry. These are 2 different people. They actually didn't really work together, but they independently came to the same results. I think Bronsted in 1908 and then Lowry in 1917. Bronsted Bronsted and Lowry. All right. And what did these two people say? Bronsted and Lowry. I'm all mixed up today, sorry. Scratch that out. That's why I didn't put notes in for you, because they'd be all mixed up. I'm getting ahead of myself with Bronsted and Lowry. Actually, before Bronsted and Lowry, two guys developed something, and this is something we're going to use a little bit today. And these are two people by the name of Henderson and Hasselbalch. Henderson and Hasselbalch. Henderson and Hasselbalch. All right, Henderson and Hasselbalch. And they developed the equation independently at different times, but they came to the same conclusion. And they developed the equation of acid, or an equation of acids. And we're going to dive into that equation here in just a little bit. And then after these guys, this is when Bronsted and Lowry came up with a slightly different definition than Arrhenius. They actually expanded upon what Arrhenius started. And this is the definition of acids and bases that we are primarily going to be using as paramedics. There are different definitions out there, and I'll mention them, but this is the primary one that we're going to use, the Bronsted-Lowry. And what they said was acids, okay, donate protons. Right, so something dissolves in water and it donates a proton. What is a proton again? It's a hydrogen ion, right? All right. So an acid is anything that donates protons, and bases are anything that accept protons. Are you guys okay with that? Does that make sense? Okay with that? All right. So do you see how this is very similar to Arrhenius, the Arrhenius definition? It's expanded a little bit. So what we're going to do today primarily is we are going to be using the Bronsted-Lowry definition of acids and bases and the Henderson-Hasselbalch equation, and we're actually going to develop some understanding of acids and bases and how this works in the human body and human physiology. But I do want to just briefly mention there is another definition of acids and bases, and this definition is a little broader, and it actually is a definition that does not involve hydrogen ions per se. And this is a chemist by the name of Lewis, a very, very famous chemist, very critical for developing organic chemistry. But Lewis also has definitions, and Lewis, the definition of an acid, all right, is anything that will accept a pair of non-bonding electrons. Okay, this is what's referred to as a Lewis acid, and the Lewis base is anything that will donate a pair of non-bonding electrons. All right, so how does this work? Well, let me give you some examples here. First of all, would a hydrogen ion meet the definition of a Lewis acid? Let's just start there. would a hydrogen ion meet the definition of a Lewis acid? Well,
Except the pair, it wouldn't accept the pair.
well, let's think about this. Let's actually think about this. So what do I have? If something is a Bronstedlowry acid, what has it done? It has donated protons. Would you guys agree? So let's say that I have water molecules. All right. So I have water molecules, and then I have an acid that has donated protons. And so I have H pluses dissolved in this water. You guys okay with that? Okay. So how many electrons does oxygen have in its valence shell? Just remind me. How many electrons does oxygen have in its valence shell?
6.
6, right? And we didn't specifically talk about this, but the electrons tend to pair up, okay, in the valence shell. They tend to pair up. And the reason that they do that is they have a quantum mechanical property known as spin. And when they pair up, one can spin in one way and one can spin in the other way, right? Plus half, minus half, or spin up, spin down. And when they go into that configuration, the overall energy decreases. And remember, nature likes to go to lower levels of energy if possible, right? So the pairing of electrons is what leads to this concept or the spin, right? The electrons going into different spin states is what kind of gives us this concept of pairing. So when we look at oxygen, right, we have how many electrons again?
Total?
In the valence.
6.
6, right? So I've got 1, 2, 3, 4, right, that pair up. And then I've got 2 all by themselves, right? They can't pair up because I need a total of 8 to have 4 pairs, right? Right? You guys okay with that? All right. So this is kind of what I have. And then when hydrogen comes in, hydrogen has 1 electron, right? Now hydrogen would like to have 2 electrons, right? Because the duet rule will be met, right? 2 electrons would meet the hydrogen's duet rule. But instead, it can share its electron with oxygen. You guys okay with that? And of course, that's just the covalent bonding that we've talked about already. So you get a structure that looks kind of like this. I have the hydrogens sharing their electrons with the oxygen down here, right? And then I have these 2 pair of electrons up here. You guys okay with that? Okay. So here I have a hydrogen ion that is dissolved in that water, and it's positively charged, right? Well, what did we just say about water? What kind of molecule is water? It's polar, which means this area is more negatively charged, right? Whereas this area is more positively charged. You guys okay with that? So that positively charged hydrogen ion, where is it go? What part of the water molecule is it going to be attracted to? It's going to be attracted up here, down, up on top, right? And what's going to happen is it's going to be attracted to one of these pair of electrons up here. You guys okay with that? And these pair, are these bonding or non-bonding electrons? They're non-bonding, right? They are not involved in covalent bonding. And so let me ask you a question. Has this hydrogen ion accepted this pair of electrons? It's become attracted to them. Yes or no? Yeah. So does this meet the Lewis definition of an acid? Absolutely. Does that make sense? How? Right? It's nuanced, but it makes sense, hopefully, right? Okay. But more things than just hydrogen ions can do this, right? So there are more things that can potentially be acidotic. For example, let's take an aluminum ion. Al plus 3. So that's an aluminum that has lost 3 electrons. Now this is something that you guys have probably never seen before, right? We've talked about this. And where is aluminum in the periodic table of elements, or aluminium, however you want to announce that, in the periodic table of elements?
Transition metals?
It's in the transition metals. And what would I say about those transition metals? Huh? Oh, well, it depends on, yeah, they're kind of the super sexy swingers of the elements, right? They're pretty crazy about their electrons. And so for aluminum to have a plus 3 charge, that means that it has gotten rid of 3, is given up 3 electrons. Well, that's not unusual for the transition metals, right? Some of them can do that very, very easily. All right, so if I have Al plus 3 and I dissolve Al plus 3 into water, and it definitely will dissolve because it's an ion. Let me ask you a question. Is the aluminum plus 3 going to be attracted to the hydrogen part of the water or the oxygen part of the water? Well, it has a plus 3 charge on it.
So the oxygen part?
It's going to be attracted to the oxygen, right? Because that's where the negative, most of the negative charge is, right? And so it's the same thing. It's going to be attracted to one of these pair of electrons. So Al plus 3 is also an acid, right? By the Lewis definition. Now, again, we're not going to focus on Lewis acids and bases in this class. Our focus is primarily going to be on Bronstedlowry, but I want to bring that up because there are broad, more generalized definitions of acids and bases. You guys okay with that? Okay, cool. All right, so now we know what an acid is. An acid, by the common definition that we're going to use, is any substance that, when dissolved in water, donates protons. And then a base is going to be any substance that, when dissolved in water, will accept protons. You guys okay with that? Okay, cool. That's what acids and bases are. So now the next question is, well, now that we know what an acid is, now that we know what a base is, how can we measure? Like, how do we measure acids and bases?
Like the pH scale?
Okay, but where does that come from? Other than it's a scale of numbers. Like, where does it actually come from? Like, what's going on there? Well, it all goes back to Avogadro's number again. So, all this goes back to Avogadro's number. So, if I dissolve 1 mole of hydrogen ions, or protons, in 1 liter of water, all right, that is the same thing as saying what? That I have dissolved 6.02 times 10 to the 23 ions, hydrogen ions, in 1 liter. You guys okay with that? That's 1 mole per liter. We know that. Here's the thing. Do we ever see concentrations of acid that high in human physiology?
Oh.
No, that's ridiculously high. Yeah. That's so ridiculously concentrated that it would be completely and utterly incompatible with life, right? It's just too concentrated. So we don't use moles per liter in the conventional way, right? Instead, what happens is it's a fraction of a mole, right? So we might use, so with scientific notation, right, 10 to the 4 is going to be a 1 with, right, and the decimal point does what? Moves over 4 times, right? Makes sense? Right? But what if I had 10 to the minus 4? What does that mean? Good. The decimal point moves to the left, right? So that's 0.0 0.001. You guys okay with that? Right? So anytime I have a negative, the decimal moves in the left direction, and anytime I have a positive, it moves in the right direction. That makes sense? Okay. So really, in human physiology, what we tend to deal with is we tend to deal with very small concentrations of hydrogen ions. And so we might have, like, say 10 to the negative 7 of 6.02 times 10 to the 23, right? So I'd have 10 to the negative 7 of a mole, something like that would be more reasonable. Well, let me ask you a question. If you're in the hospital and somebody comes up to you and says, hey, the patient has 10 to the negative 7 of 6.02 times 10 to 23 hydrogen ions per liter of solution, what is your brain going to do? It's going to go, doesn't compute, that doesn't make sense to me, right? It just doesn't make sense. This is too small. Well, it's a very small fraction of a very large number, right? It's not intuitive for us. Does that make sense? So is there something we can do to make this more intuitive? Well, what we can do is we can take this concentration, right? So I have 10 to the negative 7 moles per liter, right? And what I can do is I can take the logarithm of that. And there are many different logarithms that we can use, but the one that we use primarily in medicine is base 10. We use the log base 10. And essentially what a logarithm is, it is a way of simplifying very large and very small numbers. Okay? So for example, if I have 1,000, right? I could ask the question, how many times do I have to multiply 10 to get to 1,000? Well, what's 10 times 10? And if I multiply that by another 10, so it's 10 times 10 times 10. So how many 10s do I need to get to 1,000? 3. So if I take the log base 10, which we're using here, of 1,000, that would be 3. Does that make sense why I need 10 times 10 times 10, right? So I've taken 1,000 and I have condensed it to a smaller number, right? What if I had, say, 10,000? What would be the log base 10 of 10,000? 4. How about 100,000? Say again? 5?
5.
How about 1,000,000? 6. Right. 10 million would be 7. 100 million would be 8. 1 billion would be 9, and so on and so forth. So you see how I can simplify these really large numbers into just a single number, right? And the same thing, if I have 1/1000th, right? Well, I would move the 10 the other way, right? So that would be 1, 2, 3, right? 3. So that would give me, instead of 3, that would just give me -3, right? Does that make sense? I'm dividing by 10, right? So 1/1000th, right? And 1/10,000th, 1/100,000th, 1/1,000,000th, 1/10,000,000th, 1/100,000,000th, 1/1000,000,000th, right, would be -4, -5, -6, 7, 8, 9, and so on. Does that make sense? You guys okay with that? So it's a way of simplifying very large numbers and very small numbers. You guys okay with that? So what we do is we take the negative log. So instead of the log base 10, we just take the negative log. And hopefully this will become pretty obvious. So if I have 10 to the -7 moles per liter of hydrogen ions dissolved in a liter of water, what would be the negative log base 10 of 10 to the negative 7? Huh? Well, remember in math, what happens when you have negatives and negatives dividing or multiplying? They cancel out. The negatives cancel out, and I always get a positive number, right? So I'm going to get a positive number, and I'm just going to get what? I'm going to get 7. Right. That's the beauty of taking a negative log. Remember, with acid-base balance, we're dealing with these really small numbers, right? I'm dealing with 10 to the negative 7 moles per liter. And guess what? The negative log base 10 of the hydrogen ion concentration is, in fact, something known as pH. That's how we get pH. So 10 to the negative 7 ions, hydrogen ions per liter, is a pH of 7. Does that make sense where pH actually comes from? Now, because pH is a logarithmic, it's a base 10, right? If I move a single number in either direction, so if I go up to 8 or I go down to 6, right, the concentration is increasing or decreasing by how much? By 10 times, right? A factor of 10. So the difference between 7 and 8 is 10 times, right? If I go to 9, the difference is going to be not 20, because it's 10 times 10 times, right? So it would be 100. Does that make sense? This is a base 10 logarithm. And then if I go from 7 to 10, it's 10 times 10 times 10, or 1,000, right? Does that make sense? And there is this a word or a phrase that is known as an order of magnitude. Have you ever heard of that before? An order of magnitude? And that means 10 times. So when we say something is an order of magnitude more concentrated or an order of magnitude stronger, what we mean is that it's 10 times, right? You guys okay with that? Now, this is not the only place where this comes up. This comes up a lot of different times in science. For example, when we measure the strength of earthquakes, there's something called the Richter scale, right? And if something registers a 5 on the Richter scale, right, that means something. But what if I have an earthquake that measures a 6 on the Richter scale? It's 10 times stronger than 5. It's the same thing. It is a logarithm, base 10. Does that make sense? Now, because this is a negative logarithm, because we're taking the negative logarithm, the way that this works is, the smaller the number down here, the larger the actual value. Does that make sense? So moving in this direction is more concentrated, more acidic, and moving in this direction is more basic or less concentrated hydrogen ions. Does that make sense? And does that make sense why the pH scale is this way? You ever wondered, well, why do larger numbers indicate lower acid concentration? Well, this is why, because we're actually taking a negative log of this small number, base 10. Does that make sense? Hopefully that helps with the confusion, if there was any, right? And hopefully that explains where the hell this thing came from, right? Because you guys probably learned, oh, it's a scale that measures acid or something like that, right? Well, now we know. We actually have a much better understanding of where the hell this thing comes from and what it actually means, right? So a pH of 7 would mean that I have 10 to the negative 7, and a pH of 6 would be 10 to the negative 6. Well, 10 to the negative 6 is 10 times larger than 10 to the negative 7, right? Does that make sense? Hopefully. It's like, it was an explosion in my brain when I learned this in chemistry, when I had to take chemistry. It's like, oh my God. Okay, that makes sense. All right. So, 7 is what we consider neutral. And what I mean by neutral is a neutral solution has more or less an equal number of hydrogen ion, equal number of acid and equal number of base, right? There's a balance there. Now, where does human pH lie, however?
7.5.
Good, so it is slightly more alkaline, and you guys probably learned that the normal range, and this is an important concept to learn now, the normal range, not the normal value, not perfectly normal, but the normal range is 7.35 to 7.45. All right, so slightly alkalotic. You guys okay with that? Now let me ask you a question. You guys probably learned that the pH scale goes from 1 to 14, right? You guys okay with that? Now, is that as far as it could go? Not necessarily, right?
You go on forever.
Yeah, you could be, so what a pH of 1 actually means is, so 6 is -6, 5 would be 10 to -5, 4, 10 to the -4, 10 to the -3, 10 to the 2, 10 to the negative, what's 10 to the -1 is just 1, right? So this would be 1 mole per liter at 1. But I could get more concentrated than 1 mole per liter, right? But this is so freaking acidic that we don't see this, right? We don't see this in biological systems. And likewise, this is so incredibly basic that we don't see it. But you could get more basic than this, and you could get more acidic than that. Make sense? Okay. You guys feel like you need a break? I feel like you need a break. We're all coming up on an hour. Let's get you guys out of here on a break.